Okay, we're going to get to the section 4 of chapter 2. The logic of compound statements continues with some application. And for those of you that have had digital logic, this will be just a simple review, maybe another way of looking at things. I'm not sure. But black boxes and gates. Combination of signal bits, ones and zeros, can be transformed into other combinations by means of various circuits. Because a variety of different technologies are used in circuit construction, computer engineers and digital system designers find it useful to think of certain basic circuits as black boxes. Like an AND gate or an OR gate. What's going on inside the gate is not really relevant. You can think of it as a black box. As long as the input signals generate predictable output signals, everything should be fine. How it works on the inside doesn't really matter that much. Inside the black box is the detailed implementation of the circuit. Just like I said, focus on input signals and output signals. The operation of the black box is specified by an input-output table, kind of like a truth table. Like this, like the previous one, this has 3 inputs, so it would have 8 combinations and one of inputs and 1 column for the output. So you would construct the input-output table like this, and this is just as an example of what the output could be for such a circuit. Let's see here. The basic gates are the NOT gate or inverter. 1 input, 1 output, inverts it. So if it's an input, it's a 1, output's a 0, input's a 0, output's a 1. So pretty simple. AND gate is a circuit with 2 inputs and 1 output. If both input signals are 1, then the output is 1. Otherwise, the output signal is 0. The OR gate has 2 input signals as well, 1 output signal. If both signals are 0, then the output is 0. Otherwise, the output signal is 1. From these 3 basic gates, you can construct any logic circuit you want. These are the input-output tables of each one. They correspond to the truth tables of the AND, OR, and NOT truth tables that we covered in the previous 3 sections. Just substituting a 1 for true and a 0 for false. Otherwise, they're identical. Rules for combinational circuits. Never combine 2 input wires. If you have two inputs, I'm just going to give an example here. If you have 2 inputs and you tie them together to go to, say, an AND gate, if this one is low and this is high, you'll get a short circuit. It won't trigger the input of the AND gate. You'll get a short circuit, things will start smoking, and we all know smoking is bad for you. So don't tie inputs together. Let's go back to the, oops, not that. Where did it go? Where did my, come on. There it is. So never combine two input wires. A single input wire can be split part way and used as an input for two separate gates. So you can split an input and go to two different destinations. An output wire can be used as an input for another gate. And no output of a gate can eventually feed back into that gate. Now this is not the case with sequential circuits where there is feedback into the system. But for combinational circuits, you don't have the feedback into the inputs of the gates. The input-output table for a circuit. If you're given a set of input signals for a circuit, you can find its output by tracing through the circuit gate by gate. For example, this circuit. It would be an AND, but you're inverting the P, so it would, it would be high if the P is low, because then this would be high, and Q is high, or 1, so it would be two ones going into the and R would be a 1. Now for the input signals for this one, if P or Q, so that would be high because one of the inputs is high, the P. Then you invert that to low into an AND gate. R is 1, but both inputs of the AND gate have to be 1 for the output to be 1, so the output would be 0. So you move left to right through the diagram, tracing the action of each gate, and get the result. Come on. Likewise with this, or 1, inverted 0, and then 0 on the AND gate. Now you can do a full input-output table for a circuit, doing the same thing by just tracing each combination of inputs to the output column. So the four possible combinations of input signals for this circuit ends up being this. So the Boolean expression corresponding to a circuit. In logic, variables such as P, Q, and R represent statements, and they have only two values, true or false. Statement is the variables with connectives. Any variable, such as a statement variable or an input signal, that can take on only one of two values is called a Boolean variable, or bool, as I believe it's called in C++. And the expression is composed of Boolean variables and Boolean operations, and is called a Boolean expression. Find the expressions that correspond to the circuits below. Black dot indicates a connected wire. Crossing without a black dot means that the wires do not touch. For those that haven't taken digital logic yet. So, Boolean expression. You have P or R. Or Q, sorry, my mistake. And that's that quantity, that's this. And then that is ANDed with the AND of P and Q. P and, oops. And that P and Q is inverted. So, see, I did that work from the left to the right. And each gate, their operation is put in parentheses to indicate which is associated with which. So for this one, let's see here. Let me annotate this a little bit. There we go. So you can see where the various gates correspond to the connectives. And for this one, you have P and Q and Q in parentheses because it's a gate, ANDed with, because that's where the output goes, not R. So there goes here, there goes here, and here goes, come on, not highlight, goes here. See how that works? Pretty simple. Just putting the symbols based on the gates that you see. Yeah. Oh. So this is the way they do it. Trace through the circuit from left to right, indicating the output of each gate symbolically, and then combine them in the expression. This first one was the a configuration for the exclusive OR, which in digital logic is that symbol. So this is an implementation of the exclusive OR. I didn't show this on that table I gave last week with the various symbols that are used in different disciplines. In Boolean expressions with exclusive OR, the symbol is a plus with a circle around it. So that's the so if you see expression with the plus with a circle around it, that means it's the exclusive OR. It's similar to the OR, the plus, but has the circle around it. But you'll see that in data sheets periodically. All right. And likewise, the second circuit expression. A recognizer is a circuit that outputs 1 for exactly one particular combination of input signals and outputs 0 for all the other combinations. So if you're looking for a particular combination, you create a recognizer, and it will output high for the combination that you're looking for, and 0 for all other combinations. Like this is a recognizer. It outputs 0 to all these, well, and 1 for that one particular combination. It can't be just P and Q, because P and Q with R should also be 0, so it has to be P and Q and not R for it to be to recognize that particular combination of inputs. Okay? All right? The circuit corresponding to a Boolean expression. Well, you construct a circuit corresponding to a Boolean expression, basically the opposite way you do a Boolean expression from a circuit. You move, it's the opposite process. You move right to left instead of left to right. So you have P and, not P and Q, or not Q. So you have your outer operation is an OR. So you have that, draw your OR gate, and that's your output. That's your final out. And you do come on. There you go. You invert the Q. So you draw an inverter for the Q input, and then the other input for the OR gate is an AND gate with an inverter for P and Q here, and this ties to Q as well. So you work from the outside of the parentheses inward, and you construct it right to left, the opposite process as the creating a Boolean expression from a circuit. Oh, yeah. You got to have the inputs, outputs going to the proper inputs. But yeah. So I'm not going to do this bigger one. You get the idea from this right here. But let's see here. It's having you write the input variables in a column on the left side of the diagram. Since the last operation executed when now evaluated is an OR gate, it's in the extreme right. Like I said, then the one input of the gate is the AND operation, and the other input is the inverter of Q. The invert of Q. So there you go. To start constructing this circuit, let's see here. We didn't cover that one. But it's basically a 5-input AND gate. You're ANDing all the inputs. But finding a circuit that corresponds to a given input-output table. This is a little bit more tricky. Suppose you have this input-output table. How do you go about finding the circuit for it? Well, you start by looking at where the rows that have ones in them. In this case, 1, 3, and 4. For each row, construct an expression, an AND expression that produces a 1 for the exact combination of input values for that variable, and a 0 for all other combinations of input values. So for row 1, it's P and Q and R. In 3, it would be P and Q, P and not Q and R. And then for row 4, it'd be P and not Q and not R. So you have those 3 expressions, then you OR them together because you want one or the other inputs. So you do OR gates, you OR operations between them. And then the corresponding circuit goes with it. This operates under the assumption that you have 3 input AND gates available and a 3 input OR gate available. This is a disjunctive normal form or sum of products. If you've taken digital logic, you should be familiar with that term. But it's a disjunctive form in math uses the term disjunctive form. Sum of products is used more in digital logic. But it's called the sum of products because in digital logic notation, the ANDs are stars, like multiplication, and the ORs are pluses. So these products are summed together, so it's the sum of products. So that's if you're using that type of notation. All right. Now, simplifying combinational circuits. Consider these 2 combinational circuits. Are they the same? If you trace through circuit A, you get the following, or that input-output table. Okay? And since it's the same as an AND gate, they are the same. But you could use, okay, two logic circuits are equivalent if and only if their input-output tables are identical. You could simplify this circuit into this circuit by finding the Boolean expression and then show that the expression is logically equivalent. In digital logic, that is called using Boolean algebra, but it's the same principles in the math class environment with different symbols. The distributive law gets those out, and the commutative law, then the negation law, then the identity law. So you can work through the expressions and simplify them that way. So they are the same. NAND and NOR gates. They touch on these a little bit in digital logic, if I'm not mistaken. But these gates, a NAND is like an AND gate with an inverter following it, and the NOR gate is like an OR gate with an inverter following it. So the input-output tables of a NAND gate and NOR gate are the opposite of their non-negative counterparts. So in math, the NAND is represented by the Sheffer stroke, or vertical bar, and a down arrow for the NOR. The symbols are the AND and OR symbols with the bubble on the output. The bubble indicates an inverted output. So it's an AND gate with an inverted output. Or an OR gate with an inverted output is the NOR gate. Now, these two expressions, or four expressions, are different ways of showing things. So a not P is also the same as P NANDed with itself. And an OR is the NAND of the inverted inputs. So from this, you can kind of deduce that this is an inverter. And this is an OR gate. And doesn't show this on here, but also the AND gate. So you can get the three basic gates just using a NAND gate. That makes it what's called an universal gate. You can use NANDs for any combination, just NANDs for any combination of digital logic circuit. So this shows the process of deriving the equivalences for an inverter and an OR operation using just NANDs. And that's it, yeah. Also, the NOR gate is also a universal gate. In a similar way, you can construct, using just NOR gates, any logic circuit. So that's the 10-cent tour of digital logic. I'm sorry a good chunk of you are bored with this because you've already taken digital logic. This is all just, yeah, get on with it. Going to be more of the same in section 5. More review for those digital logic graduates. Come on. Cooperate. Logic of compound statements and the number systems and circuits for addition. Remember number systems from digital logic? And go through them again. Representations of numbers. First with binary. Okay. Any integer greater than 1 can serve as a base for a number system. In computers, base 2 or binary notation is of special importance because signals in modern electronics are almost always in one of only 2 states. I use the Latin root bi. It's not a root, it's a prefix, not a root. But anyway, little detail there. The binary notation of integers from 1 to 9. So you can only represent two different numbers with binary. So you have 1. You add 1 to 1, you get 2, but you can't. There's no 2 in binary, so you have to carry the 1. So you get 1, 0. 1 plus 1 equals 10. Argue that with your 5th grade math teacher. Add 1 to that, you get 3. Add 1 to that, 1 carry the 1 is 0. Or 1 plus 1 is 0, carry the 1 is 0, carry the 1. And so on and so forth. You get 1, 0, 1 for 5, 1, 1, 0 for 6, 1, 1, 1 for 7, 1, 0, 0, 0 for 8, and 1, 0, 0, 1 for 9. Those 10, that and 0 for 0. those 10 digits are sometimes referred to as BCD, or binary coded decimal. If you see only those 10 combinations of ones and zeros, it might be binary coded decimal, which some computers will use. So, oh, come on. Why aren't you cooperating? All right. So, technically, what's going on in the conversion from decimal to binary is the addition of powers of 2. You take the base of the number system you're using, and each place is a power of that base. So the first position is 2 to the 0th power, or ones. The second position is 2 to the 1st, or 2's position. Third position is 2 to the 2nd power, or the 4's position. And so on and so forth. I guess, like I said, this is kind of the 10-cent tour of number systems as well. They get more in more detail in it in digital logic. I'm just spending half a class on it, so I'm not going to get too detailed into the theory of it. But knowing the powers of 2 is handy for number conversions and general computer science and computer engineering, knowing how many combinations there are given a number of lines or columns. These are the powers of 2 up to the 2 to the 10th. So if you have if you have one line, you can have if you have one line, you can have 2 combinations, 2 lines, 4 combinations, 3 lines, 8 combinations, so on and so forth. So a 64-bit computer, like the ones that are at your desks or are typing on or whatever, would have 2. Come on. All right, come on. There we go. 2 to the 64th power combinations of addressable space. A long time ago, there was the Windows operating system was only 32-bit, and therefore could only address what is that? Approximately 4 billion. It was a 32-bit processor, so it could only address about 4 billion memory address locations, and it could only count up to, conveniently at least, about 4 billion to about 4 billion. So if you had a file that was 5 gigabytes, like a large video file, Windows didn't know what to do with it. It would give you a negative number in the in the file size. When you look at the file size, it would give you a weird negative number. And you can't have a negative number for a file size, so it was kind of screwy. But when Windows and other operating systems went to 64-bit, what is 4 billion squared? Or no, not squared. Is that, yeah, 4 billion squared is what, some astronomically huge number or something like that. It's you don't have that problem with running out of addressable memory space or file size numbers or anything like that anymore. But yeah. So knowing the powers of 2, you are not cooperating with me today. This is not nice. Oh, come on. Okay. So represent 110101 in decimal notation. You take the powers of 2. So you have 1, the 1's position, 2's, 4, 8, 16s, and 32s, right? So you take 1 times 32, 1 times 16, 0 times 8, 1 times 4, and 1 times 1 gives you, what, 53? That's how you convert 1s and 0s to decimal. The simple way, at least. But yeah, you multiply by the appropriate power of 2. Now represent 209 in binary. Well, 209 lies between 256 and 128, so you put a 1 in the 128th spot. Subtract 128 from that. You get 81. Oops. Okay. 81 is between 64 and 128. So put a 1 in the 64's place. Subtract 64 from this. What is that? 17? Yeah, 17. 17 is the result there. There's no 30. This is less than 32, so there's nothing in the 32's place. There's a 1 in the 16's place because it's greater than 16. So to subtract 16, get 1. And then there's nothing in the 8's place, 4 place, 2's place, but there is a 1 in the 1's place. So that should be the binary representation of that decimal number. Let's see if I did that right. Yeah, going through the process of that, and so you get 11010001. There you go. Addition and subtraction. I kind of already went over that a little bit. Works just like with binary. It works just like decimal. If you get to a number above what can be represented by the system, you roll over to 0 and carry the 1. So 1 1 0 1 and 1 1 1. 2 is 1 0. 2 is 0 1. That's 3. That's 1. Carry the 1. And that's 0. Carry the 1. 1. Pretty simple, straightforward. Like I said, it works the same as in decimal. Just you're rolling over at 1 instead of 9. Or rolling over at 2 instead of 10. So 1 0 1 0 0. Okay? I'm going to skip the subtraction because this shows this borrowing and all that sort of stuff. There's just an easier way of doing that. So, well, I'm going to skip the subtraction part of math with binary. Now, circuits, we'll revisit the subtraction in just a minute. Circuits for computer addition. So the circuit for producing a sum of binary digits has 2 outputs, not just one. It has the sum and then the carry, because 1 plus 1 equals 1 0. So you have to have 2 outputs if your 2 inputs are 1. So you have the exclusive OR to express the sum, because 0 plus 0 is 0 in the sum. 0 plus 1 is 1 in the sum. 1 plus 0 is 1 in the sum. And 1 plus 1 is 0 in the sum with 1 in the carry. So that corresponds to the exclusive OR for the sum, which is this expression here. If P and Q are both high, then the carry is high as well, a 1. So that corresponds to an AND gate. So there is the AND gate going to the carry. So this is a exclusive OR, and this is an AND. The AND gate is performing double duty. So there you go. And that is called a half adder. It is called a half adder because a full adder takes a carry as an input, a third input. The carry needs to be input into the next bit, addition into the next bit. So, for calculating the next bit. So, what a full adder is 2 half adders, where you add 2 bits together, then add the result to the third bit, making a full adder. So here is the block diagram for a full adder, where the let's see here. Generally, you'll see these as A, B, and C in, and this is C out and sum. So they're just using P, Q, and R, and C and S as inputs. But the A and B input, and then the C carry in from the previous previous circuit is brought in, and then the carry out and sum. How these are linked together is you have your binary numbers. You have say this is A1, A0, B0, A1, B1, and A2 and B2. And you have your sum 0, sum 1, sum 2, sum 3. So take two binary numbers, A and B, bit by bit, the two 0 bits into a half adder, the two 1 bits into a full adder with the carry from the half adder, and the two 2 bits into a full adder with a carry from the previous full adder. This is what's called a ripple adder. I've never heard of it called a parallel adder, but they say it's called that. But in digital logic, it's typically called a ripple adder because the result down here cannot be calculated until these previous results have been calculated. Therefore, the result ripples down from the low bits to the high bits. So that's a ripple adder or parallel adder. But anyway, now this is where subtraction comes in. Subtraction is just adding a negative number, making a number negative, and then adding it to the previous number. Negative numbers are represented as by 2's complement, a system called 2's complements, and that represents signed integers. Typically, a fixed number of bits are used to represent integers on a computer. Like I was talking about earlier, 32 old computers are 32-bit, modern are more 64-bit. But the leftmost bit, the high bit, is typically used to represent the sign of the number. Two's complement is a number for 8-bit. Two's complement is an integer between negative 128 and positive 127. It gives you a weird way of doing. The book gives you a weird way of finding the 2's complement. There's an easier way, but the easiest way to do it is to flip the bits and add 1. So if, let's see, okay, 8-bit 2's complement for negative 46. Take the absolute value, represent that in binary. So that's a 1 in the 32's place. 32, that's 14, so 0 in the 16's place, 1 in the 8's place, 1 in the 4's place, 1 in the 2's place, 1 and 0 in the one's place. Okay, so that's the binary representation of 46. For 2's complement, to make it negative, you flip the bits, then you add 1. That's 0, 1, 0, 0, 1, 0, 1, 1. And that is the 2's complement representation of negative 46. Let's see if I did that right. Yeah, I did it. I did it right. Okay. Oh, whoops. So represent it in, add the absolute value, flip the bits, add 1. Now, the nice thing about this is you can add that number to another number, and it's the equivalent of subtracting, in this case 46, from the other number. So, because, like I said, subtraction is just adding a negative number. So it works out. Let's see here. Here's how the facts are used when they. Yeah. Not gonna worry about that. The leading bit 127, represented by this binary number, is the largest integer you can represent with 8-bit 2's complement, because the leading bit is the sign bit. 0 indicates a non-negative number, and a 1 in the most significant bit location would indicate a negative number. Now here's a representation of how things go with 2's complement. 0 is the same, and positive numbers are the same as regular binary. But when you subtract 1 from 0, they all roll over to 1s, and you count, you subtract 1 from each bit, from each number, to get to negative 128, the smallest integer with 8-bit 2's complement. We already went through this. What is the decimal representation of for the integer with 2's complement? 10101001. Well, again, you flip the bits. 0, 1, 0, 1, 0, 1, 1, 0. Then you find the decimal value of that, and because it had a leading 1, put a negative in front of it. So take the decimal value of, forgot to add 1. So take the decimal value of this add a negative sign in front of it, and you have the decimal number. How are we doing on time? Okay. Got a few more to cover here. Now, we'll skip all that. Addition and subtraction with 2's complement works the same way. You can add a 2's complement negative number to another number, and you're effectively subtracting it from the first number. Let's see here. I'm gonna leave the main theory for all that to digital logic, or if you haven't taken digital logic yet, review the slides more carefully when I post them on Canvas this evening. Did I post the last lecture's slides to Canvas? Not the slides? Okay, I'll do the rest of chapter 2 this evening when I get home. So, but yeah, a minus b equals a plus negative b for all real numbers. So we're adding a negative number to a number is effectively subtracting it. Let's see here. So add 78 to negative 46, and you get 32. In the addition process, you might have a spare 1 hanging off the side. Ignore it. It's just an artifact. It's not part of the result. So you just add the 2 numbers together, the negative to the other number, and that's how you get subtraction. Let's see here. Yeah. This is just the addition and with 2's complement. Now we get to hexadecimal. Let's see if I can get through this pretty quickly in the next 10 minutes or so. Hexadecimal is base 16. So it's more complex than, or more compact than decimal, because each digit can be arranged in the range of 0 to 15. And again, they're using the word root when it's a prefix, not a root. Hex and deci are prefixes, not roots. But anyway, so each decimal or each hexadecimal location represents a power of 16 because that's the base. So here's the hexadecimal digits. You run out of normal decimal digits, you would go to A, B, C, D, E, and F. The handy thing about hexadecimal is it neatly corresponds to a 4-bit combination of binary digits. And that is the 4-bit combination correspondence. So the 64-bit numbers that the modern computer can handle, if you try to write those numbers out 64 places, that's the width of a page for one number. Whereas in hexadecimal, each 4 bits acts as it can be taken up by one hexadecimal digit, and therefore 64 bits would be represented by 16 characters instead of 64. Yeah, 16. So I'm not going to go through the process of, I don't have the time to go through the process of converting 3CF to decimal notation, but the process is basically the same as binary. 16 to the power of 0, power of 1, power of 2, and multiply it by the value in those locations and go from there and add them up. Now, hexadecimal to binary is just a simple swapping around of the bits versus the hexadecimal digits. So B is 1, 0, 1, 1. 0 is 0, 0, 0, 0. 9 is 1, 0, 0, 1. And F is 1, 1, 1, 1. See? See? That's B, 0, 9, F. Much more compact. So writing large numbers in hexadecimal is more efficient. So there you go. Let's see here. Convert an integer to binary to hexadecimal is basically the same thing. If you don't have an even number of a number evenly divisible by 4, you pad it on the left with zeros, unless that it's a 2's complement negative number, in which case you pad with ones in front of the with leading ones in front of the number. So hexadecimal notation. What do we got here? We got 1, 2, 3, 4. So we got 9, A, C, and 4. Right? Eventually you get used to the converting back and forth between hexadecimal and binary, and you'll memorize the binary combinations for each of the hexadecimal digits. And conversions like this will be pretty simple and straightforward. Oh, I'm sorry, it's D, not C. Oh well. But anyway, so 4DA9. To do that, it's the smallest addressable memory unit in most computers is 1 byte or 8 bits. In some debugging operations, a dump is made of memory contents. To save space and make output easier on the eye, the hexadecimal versions of the memory contents are given rather than the binary versions. So this is an example of what a memory dump might look like. And that's what the binary would be. But depending on the content of the memory location, what does that actually mean? Could it be decimal numbers? Could it be integers? Could it be floating points? Could it be ASCII encoded text? You know, it's Uh, who necessarily knows? But I believe that is it for chapter 2. We are going to have a test on chapter 1 and 2 combined next Thursday. We'll start on chapter 3 on Tuesday. So have your notes ready for a test on Thursday in class. Have a wonderful day. I believe that's time. Yeah.